When we're headed in a particular direction, we occasionally have to stop, wait for little bicyclists to cross if necessary, and then turn in a perpendicular direction prior to continuing in our intended direction. We would say that our path became discontinuous. Functions can also become discontinuous at a point within an interval. In this video, we'll examine discontinuity in functions using the limit process. Hi, I'm Dr. Ron, and welcome to my channel. Before we get started, please remember to like this video and subscribe to my channel. Subscribing to my channel helps support this channel so I could continue to bring educational content to you. And please watch the entire video to the end for a little surprise. Now let's get started with continuity. There's a very famous photograph of this fence following the 1906 earthquake. As you can see, the earthquake caused what used to be a continuous fence to become discontinuous by several meters. Because the photograph is copyrighted, I made this sketch. But it illustrates the point. If a squirrel were to run along the top of this fence, that squirrel would have to make a jump in order to continue running along the fence. We call this a jump discontinuity. In terms of a graph, which is the easiest way to see discontinuities, we see the jump discontinuity. This looks just like the fence in Marin County following the 1906 San Francisco earthquake. There's a definite gap between the two parts of the function. Other forms of discontinuities include the infinite discontinuity, where the two halves of the function are heading up toward infinity for their range. They'll never come together because we can never get to infinity. And so this function is discontinuous at whatever this value is. You can see a similar situation where one half of the graph is going to positive infinity and the other half on the other side of the vertical asymptote is going to negative infinity. Finally, there's a form of discontinuity called a removable discontinuity. This is similar to the idea of a hole in the road that can be removed by filling it in with asphalt. And we could do something similar with a removable discontinuity by redefining the function and using that to fill in the gap, therefore now rendering the function continuous at whatever this value is. Let's call it C. Here's a question I created for this piecewise function, f of x equals sine x between 0 and pi over 2, and equals 2x minus 2 between pi over 2 and 3. And the question is this function continuous at x equals pi over 2? The first criterion that we must meet is, does the limit as x approaches pi over 2 of the function exist? In other words, does the limit as x approaches pi over 2 from the left of the function equal the limit as x approaches pi over 2 from the right of the same function? Let's see. The limit as x approaches pi over 2 from the left of the left part of this function, which is sine x, clearly plugging in is going to give us the value of 1. And we can see that on the graph. On the other hand, the limit as x approaches pi over 2 from the right of the other part of this piecewise function, 2x minus 2 plugging in, gives us 2 times pi over 2 minus 2. We notice that the 2's cancel, and this gives us pi minus 2, which we could estimate, because pi is irrational, as approximately 3.14 minus 2, or approximately 1.14. Because the limit from the left does not equal the limit from the right, we conclude that the overall limit as x approaches pi over 2 of this piecewise function f of x does not exist. And because this is true, we do not need to look at the other two criteria. We can simply conclude that f of x is not, and I'll abbreviate, continuous at x equals 1. Here I've redefined the function, or at least the second half of this piecewise function, to be 2x plus 1 minus pi. The question now is, does the limit as x approaches pi over 2 exist? From the previous example, we could see that the limit as x approaches pi over 2 of sine of x still equals 1. We're going to look at the other half of the piecewise function. What happens as x approaches pi over 2 from the right of f of x? This time we're going to use this linear function, 2x plus 1 minus pi. Again, if we plug in to this limit, we arrive at 2 times pi over 2 plus 1 minus pi, which is equal to, canceling the 2's, pi plus 1 minus pi, which equals 1. And we see, and we should write this on our exams and our homework, by the way, because the limit as x approaches pi over 2 from the left of the function equals the limit as x approaches pi over 2 from the right of our piecewise function, we can conclude that the overall limit as x approaches pi over 2 of our function exists. And in fact, it equals a finite real number 1. We have consequently met the first criterion for continuity. The limit from the left now equals the limit from the right. The second criterion asks, does the point f of pi over 2 exist? Notice that what I've done is I've redefined the function where I remove the equal sign from underneath this part of the inequality. I kind of stuck it next to the 3 just to put it someplace. If we look at this function now, we notice that at x equals pi over 2, there is no value. Consequently, at this point, f of pi over 2 does not exist. I'm going to go ahead and fill one in, let's say 1.5. I'm going to redefine my piecewise function to say that f of x equals the value of 1.5 when x equals pi over 2. Now, if we ask the question posed in criterion number 2, does f of pi over 2 exist? We can say it does. And we could state clearly what that value is, that f of pi over 2 equals 1.5. So now we've met the second criterion for continuity at a point. That leaves the third criterion, and usually math authors will often only ask the third point. Does the limit as x approaches pi over 2 overall of this function, f of x, equal the point f of pi over 2. As it stands right now, clearly 1.5 does not equal 1. So the answer to question 3 right now is no. And we could still see that the function is discontinuous at x equals pi over 2. It creates this strange jump to a point and then jump back down in order to be continuous. But what we can do is, if we redefine our piecewise function to say that f of x equals 1 when x equals pi over 2, what we have done is we have removed the discontinuity at x equals pi over 2, hence a removable discontinuity. And in this instance, we can conclude the answer is yes. And then we could state that f of x, as now defined, is continuous at x equals pi over 2. Here's an interesting problem that I made up. F of x equals x cubed minus 27 over x minus 3. And the question is this function continuous at x equals 3? We're going to go through our 3 steps, and we find the first step asks, does the limit as x approaches 3 of f of x exist? Plugging in the function for f of x, x cubed minus 27 over x minus 3, and substituting 3 for x gives us 0 over 0, an indeterminate form. That means we need to do more work. Let's use SOAP, same opposite always positive, for factoring differences and sums of cubes. What we arrive at is the limit as x approaches 3 of x minus 3 times the quadratic x squared plus 3x plus 9. This is all divided by x minus 3. That factor cancels. And by the way, I wrote out the algebraic check to make sure that I didn't make a mistake. Now I could take the limit as x approaches 3 of x squared plus 3x plus 9, which is simply 27. Therefore, the limit as x approaches 3 of f of x exists. But the next question is, does f of 3 exist? And the answer is no, it does not exist. We can conclude from this then that f of x is not continuous at x equals 3. In order to prove a function is continuous on a closed interval, we prove first that the function is continuous on the corresponding open interval, and then we check either end of the function to make sure that we can actually reach an endpoint. So, for example, given f of x equals the square root of 64 minus x squared, where we want to show continuity on the closed interval -8, 8, we note that for every a on the open interval -8, 8, that the limit as x approaches a for that function, square root of 64 minus x squared, equals the square root of 64 minus a squared. And noting that a being greater than -8 or less than +8 results in the square root of a positive number less than 64, and that's fine as long as we have a positive value as a radicand, but that equals f of a. And this proves in a very intuitive way that this function is indeed continuous on the open interval -8, 8. Looking at the left-hand point, a equals -8, we take the limit as x approaches -8 from the right, realizing that there really isn't anything coming from the left. It doesn't exist within the domain of real numbers, of the square root of 64 minus x squared. That equals the square root of 64 minus -8 squared, or 64 minus 64. That's the square root of 0, and that's simply 0. But 0 is a real number. Therefore, we can conclude that the right-hand limit exists and that this function is continuous on the closed interval on the left-hand side of -8. We do something very similar for the limit approaching the left for the right-hand endpoint, again, arriving at a real number 0 for the limit and concluding that the right-hand limit also exists. Putting all of these together, we can conclude that the function f of x, which equals the square root of 64 minus x squared, is indeed continuous on the closed interval, -8, 8. In the next video, we will continue to look at continuity involving combined and composite functions, and we will also examine a very important theorem in mathematics called the intermediate value theorem. In the meantime, I hope you enjoyed the little sketch that I presented today, and I hope to bring more art, animation, and maybe even some background music to future videos. Please remember to subscribe to this channel and like this video. Subscribing to this channel and liking this video helps support my channel. I'll see you in the next video.